Okay, so it's a pleasure to host Thierry Penduff from Grenoble. So Thierry will speak about modeling of ocean dynamics, and I think it will be very complementary to the lecture you had last week, because he will speak about the variability of the larger scale near the surface.
Yeah, thanks very much, Freddie, and the organizers for inviting me here. It's a really beautiful place and very interesting summer school. Unfortunately, I will have to leave tomorrow by noon, so if you want to talk, I'll be available until then. So indeed, I'm working on ocean physics, ocean dynamics modeling, and that's a work which has been done with a few people over the last years. And okay, it's about the low frequency variability of the ocean, of the global ocean circulation in the turbulent regime. And as I will try to convince you, we may see it no longer as responding passively to the forcing or being just coupled to the atmosphere, but it's also able to generate a strong amount of variability by itself, and this variability has a strong chaotic character, and it's more modulated by the atmosphere than directly forced by it. So when I will say chaotic, I will mean actually sensitive to slight changes in initial states. It's also intermittent, it's a broadband, irregular, intermittent signal, and I will show you a few things about that. So in this example, first of all, if you have questions, remarks, whatever, please feel free to interrupt. What you're seeing here is sea level anomalies that emerges spontaneously in a 1/4 of a degree global NEMO simulation in the eddy permitting regime, 1/4 of a degree resolution, under a purely seasonal forcing, okay, seasonal cycle, which is repeated exactly the same every year. So there is no low frequency variability in the forcing, which means no interannual and longer timescales, but such a model generates a lot of broadband frequencies, a broad range of frequencies spontaneously. Of course, you see the mesoscale, which dominates in the mid-latitudes. That's pretty well known. But you may see, I'm going to focus on this more precisely in the following, some much longer and slower variability, which is superimposed on that. And we believe there might be some implications for climate dynamics and the attribution of what we see at climatic timescales in the ocean.
Well, can we have a sense of the time scale here on the movie?
Well, I'm using successive 5-day averages, each of the frames, okay? So it's going, yeah, I should have added a time counter, but well, that's typically the translation phase speed of mesoscale eddies, okay? I'm gonna focus more on the scales afterwards. So just a quick look back in the mirror about what's been done over the last decades about these phenomena in idealized models, idealized setups, typically square basins with flat bottom, with simplified dynamics, QG or shallow water. Here is a typical wind-driven double gyre solution. And what's happening when you increase the Reynolds number under a constant or a seasonal forcing is that such a system progressively generates some oscillations, which, for instance, can be seen as a high energy Gulf Stream and a low energy with, let's say, stochastic or irregular chaotic changes between the two typical states. And when you increase further the Reynolds number, you may have additional modes coming in. So this has been documented quite a few times in simple models like this, and the typical timescale of the instabilities and modulations of this wind-driven circulation is about 1 to 10 years, the timescale of it. It concerns western boundary current systems, as you can see, Gulf Stream, Kuroshio, stuff like this, surface jets, but also deep western boundary currents at depth, 200, 2,000 meters, and associated structures like recirculation gyres that you have south and sometimes north of the jets, and they are modulated in shape and strength. It also concerns the mode waters, which sit equatorward of such western boundary currents, which are modulated in terms of volume of low PV mode waters. And you also see some large-scale modes emerging and being sustained by the system. This is a study by Hazeliger and Riffelt, and they have a small, they have a slanted domain like this. It's a double gyre. You've got here a trace of the subpolar gyre in this system, and there is a subpolar and subtropical and subpolar gyre. And they show that in their system, in their solution, they have 8 and 4 year modes which are structured in space. This one has big anomalies of isopycnal depth, that's a thermocline depth typically, which oscillates like this. So it's structured in space and it's more irregular and chaotic in time. And also the ACC is concerned, basically all the mid-latitude current systems are concerned, and there are some implications and influence of these main driving processes, current eddy topography interactions. So the jets of the ACC are modulated in terms of path and transport. You see some jet jumping north and south of topographic features and stuff like this, and spontaneously migrate equatorward. There is a whole bunch of spontaneous, intrinsic, chaotic, low-frequency variability in such systems. So there's been 2 main nonlinear ways of investigating these phenomena in the past and still today. The first is based on dynamical system theories, bifurcation studies like this, and these studies are focused on the study of spontaneous transitions between multiple large-scale equilibria. So the focus of this study is, well, what they show is that when the Reynolds number increases, the transitions between the states become more and more chaotic, and the system goes through transitions between various instabilities and modulations of the mean state. In this paradigm, the mesoscale eddies which emerge at high Reynolds number, they actually mostly provide some ambient noise, if you wish, some stochastic steering, as Isaac said this morning, I think. But they are actually not crucial. They are not investigated as a source, as a driving source of the phenomenon. And the other paradigm is that of people who focus on the eddy fluxes, where the eddies actually drive the low-frequency chaotic variability. So there's been studies about the PV fluxes, inverse cascade in time and space. And in those studies, those studies are focused on the impact of eddies in directly driving this phenomenon. When the Reynolds number increases, you've got stronger eddy fluxes. And in this paradigm, the mesoscale eddies rectify the flow and drive the low-frequency chaotic intrinsic variability. Actually, I believe that those two, I'm probably not the only one, but those two ways of thinking are complementary and provide different insight into this phenomenon. So the question, as a realistic ocean modeler, the question that came in was, how does this phenomenon look like in global, realistic, turbulent ocean general circulation models in terms of imprints on various climate indices, its strength, its origin, and its possible implications for oceanographers and climate dynamicists. So here is, well, that was the introduction. Here is the outline of my talk. We're going to talk about this phenomenon in the global ocean. First of all, we've looked at it by isolating it. We submitted such global ocean models under repeated seasonal forcing, as I showed, without any low-frequency variability in the atmosphere, and see what emerges in the system. So I'm going to show a couple examples of what's going on, the strength of its structure on sea level, AMOC. These are 2 so-called climate indices, and there are many others which are impacted, but I will focus on those 2. And just a slide on a possible generation mechanism. Then I will focus on more recent work where we wondered what this phenomenon, after being isolated, how does it behave when it's exposed to a full range of timescales in the atmosphere? You take the same model, you expose it to a full atmospheric reanalysis where the timescale goes from 6 hourly to several decades. And you see if this stuff is modified, damped, excited, whatever. So that's a goal of the Occiput project that I will tell a few words about, and we're going to see how it works on sea level, ocean heat content, and MOC. And I will tell a few words about what we are currently working on. There are new challenges that we have to face and to study this. And so let's start with this first part. So it started a few years ago. We were developing the 1/4 degree version of the global NEMO ocean sea ice model, and focusing on the, let's say, 1 to 10 year range of timescales. So I'm going to show some animations where it's been bandpass filtered. Okay, I'm just focusing on interannual to decadal. So we had altimeter observations. We had the sea level anomalies from the simulations. And in this first animation I will show you, the model is driven by the full range of timescales. So it's a atmospheric reanalysis. So we expect the model to reproduce pretty as well as possible the observed variability on these timescales again. And well, we looked at it in detail in a couple papers. And actually you see the big El Nino here in 1998. The model kind of generates the right amount of low frequency sea level variability with well located patterns, especially in the low latitude. It's more complex in the high latitudes. But typically the model, we quantified its ability to reproduce the real world. It's not perfect, but it's quite okay.
So here it's a one-way coupling, only
yeah, it's
from
forced.
the atmosphere to
I'm
to
going
the
to
ocean.
talk about atmospherically forced ocean models. It's a perspective. What's going on in the coupled system is more complicated. So these are models which are driven by the atmosphere. There is no data assimilation, okay? But I was more interested in another simulation where we take exactly the same code and we drove it by the same seasonal cycle repeated for more than 3 centuries. And okay, same bandpass filtering, and we saw that an intrinsic variability emerged around the world, especially at mid-latitudes, as you can see. It has a strong chaotic character, and the color bar is the same as here. And as you can see, the magnitude of the anomalies is quite similar. So the ocean is able to generate spontaneously without the atmospheric variability driving it, to generate a strong amount of what you see in the fully forced simulation. You also see some structured features. You cannot see completely the larger scale of this intrinsic variability. I will show you a few examples afterwards. So you have the low frequency part of the mesoscale field, as you can see here, but also some much larger features. And the strength of this signal was the main surprise, not its existence, because square basin studies had shown that it exists. But if you work in a square basin, it's difficult to say if it's strong as compared in the real world or not. We are a bit closer to the real world, and as you can see, the real world is down there, fully forced and seasonally forced up there.
Can I ask something?
Sure.
I'm here. In the previous animation, it looks like the scale of the eddies, but then on a time scale of 1 to 1.5 to 11 years.
Yeah.
Is that correct, that it's really that small scale, the scale of eddies?
Well, the eddies have this scale, and the Aviso altimeter based data set actually doesn't see the smallest eddies. So you have here only a view on the largest eddies. But indeed, the eddies in the ocean reach scales of a few kilometers, which are far from being resolved there. That's typical of the size of the eddies. In the observations, the model kind of reproduces them at moderate latitudes, but when you go at high latitudes, the resolution is not enough to reproduce real small, the actual small scale of eddies. So to quantify the intensity of the phenomenon, you can just take the variance of whatever variable you want from the seasonally forced simulation and the variance with full forcing. Yeah.
May I just ask a question about the previous slide about the equator? So you said there was an El Nino in the case with the total
Yeah.
forcing.
Yeah.
So you do not need the coupling with the feedback with the atmosphere to get it, and then it disappears completely on the case above. Or?
That's a coupled phenomenon. El Nino emerges because the ocean talks to the atmosphere and blah blah blah. But if you decouple and impose the atmospheric variability, the ocean generates a very nice El Nino. When in this simulation we have no atmospheric low frequency variability, no El Ninos, the ocean doesn't generate much. Okay? So if you want to quantify these impacts, here first of all, what you've seen so far is completely absent when you don't resolve the mesoscale turbulence in the ocean. A little bit is there, but it's extremely small. So this fraction between the intrinsic variance and the total variance is basically 0. So this map is all blue at 2 degrees with no eddies. But as you can see, this ratio, I'm focusing on low frequency and large scale sea level variability, which spontaneously emerges in the ocean. You see that something like above 50% throughout the whole ACC band in the Kuroshio, in the North Atlantic, well, something like at least 30% up to 100% in some regions emerge spontaneously with no direct forcing by the atmospheric variability. So that's a big number. And it's highly sensitive to initial state, as you will see. We computed this same ratio for the MOC in the Atlantic. So that's a real big, widely integrated climate index. You have kind of local manifestations here of this phenomenon, despite the spatial smoothing. But here we integrate zonally, so that's a bigger, much bigger time scale, space scale. First of all, this is latitude in the Atlantic, and this is the R ratio for the MOC. If you do this pair of simulation at 2 degrees, you find 0, okay? No intrinsic AMOC variability. And once you reach 1/4 of a degree, you see that, or it doesn't differ much at 1/12 of a degree. We did some pairs of simulations like this at 1/12 degree. You see that there is a southward increase of this ratio, which reaches something like 40 to 50% down there. So that's half of the variance which emerges spontaneously, and which is not directly driven by the interannual variability of the atmosphere. This is a time series of this guy, of the interannual AMOC variability, which emerges under purely seasonal forcing for 327 years. So it's, sorry for it's very small, it's minus 1.5 plus 1.5 Sverdrup throughout several centuries. So we see it's basically sustained. Yeah.
Stupid question, but what is the force of degree and 1/12 degree?
What is the?
1/4 degree and 1/12 degree. And here 2 degrees, 1.
What is the? I didn't. Oh. That's typically 200 kilometers. That's typically 25 kilometers, and that's at mid-latitude, and that's typically, yes, 10 kilometers. Okay. So that's a time series of what emerges here, and you have 1 dot per year. So there is no direct forcing of it, and that's a wavelet transform of this blue signal. And as you can see, well, you cannot see. I apologize. Years. I mean, the time scales go from 2 years to almost to 1 century, and this is time over 327 years. And you see some energy coming in and out over this broad range of scales, with the emergence here after 150 years or so of multi-decadal variability in the AMOC. So that's really a broadband intermittent complex signal which emerges despite the only seasonal forcing. So that's what we had. That is what we had at that time, and we felt it was important to investigate, okay, what can generate this, what can be the implications of this for oceanographers. So with Guillaume, who was a PhD student at that time with me, we investigated one possible driving mechanism. So you have here we focused on the 1/12 simulation. Here is a standard deviation plot of sea level, focusing only on interannual and longer timescales, with full forcing, okay, able to mimic the real world. So these are the observations of sea level low frequency variance. You see some hotspots in the tropical Pacific, in the mid-latitude, etc. And that's what the model does with no data simulation, with full forcing. So it's pretty decent, I would say. It's pretty nice. And so we decided to focus on this simulation with full forcing and with only seasonal variability. And inspired by a study by Brian Arbick, with whom we actually collaborated, we computed in the Fourier space the actual impact of the U grad U momentum advection. It's a QG formulation, but if you go in the KL omega Fourier space, three-dimensional Fourier space, you can compute the exchanges of energy between the various scales. And here is one result. So this is first, we focused in this slide, I focus on this box, the ACC. And this is a spectrum of sea level between, let's say, 10 days, I think, and several decades here. It's a 50-year simulation, so we could compute the spectra and exchanges between scales up to several decades. You see that the forcing has no impact, the forcing content has no impact on the spectrum of the sea level variability down there. It's extremely similar, and I put some two typical scales here, 5 months and 15 years. And in this plot here, we have exactly or very similar behaviors of the model with or without the interannual forcing. And this tells us that mesoscale chaotic energy, let's say mesoscale energy, spontaneously cascades towards longer timescales. So that's a temporal equivalent of the better known spatial inverse cascade.
So wouldn't you expect to have more high frequency energy in the spectrum for the fully forced case? And the fact that you don't have any, because there is some in the forcing, right?
There is some, but we are in a particularly strong eddy active region. If you go there, I would trust indeed that the forcing would directly inject some higher and lower frequency in the system there, okay? Because you have weak nonlinearities, but we focused on purpose on a very active region. But we, in the paper which is submitted, we have done the experiment, this quantification in various eddy active regions. And typically there is not much difference.
That because the dissipation is larger in this at these frequencies in the more active regions?
Well, first of all, you have a cascade, okay? Eddies which emerge at high frequency merge together, and they actually become feed the lower frequencies. The dissipation is typically the same in those two simulations. So, and it's well known that the oceanic spectra are really red on many variables. Okay.
The seasonal forcing still has daily variability?
No, but we introduced. Oh yeah, sorry. Does the seasonal forcing include the daily or high frequency forcing? In fact, no. But we average every 1st of January 2nd over the 50 years. But we included the prime terms. If you wish, the lower frequency consequences of high frequency correlations between fluxes and SSTs, for instance. So the mean states of those two simulations are very similar, and their seasonal cycles as well. But indeed, there is no daily, there is no storm in there.
One quick question. So I was wondering, what determines the slope of the inertial range for this so-called temporal inverse cascade?
Well, it depends on the regime you're in. There's been some studies about whether you're more into quasi-geostrophic dynamics or SQG dynamics. Then the change in slope is more set by dissipative processes. Yeah, there are some studies about this, but we can talk about this if you want afterwards. So the point is,
what sets the 15-year timescale for the
well, it
lower
depends.
end of the spectrum?
It depends on the region. That's in a region where this transfer I was talking about, spontaneous transfers, reaches the longest timescales. In other regions like the Gulf Stream, I think, or I don't remember which, it goes only to 8 years. In other regions, it's more like 3 years. It depends. So I have no answer to that.
So why is 15 years the longer timescale? This is just the overall length of your simulation?
No, the simulation could resolve longer timescales to some extent. Maybe if the simulation was 500 years long, it would reach longer timescales. But that's what comes in, out of the diagnostic. I have no. So that's a possible source of low-frequency chaotic intrinsic variability, directly driven by the interaction between mesoscale eddies. Okay, so high-frequency chaos generates low-frequency chaos. There are others. The literature talks about other nonlinearities in the system which are able to generate even lower frequencies spontaneously, like U grad rho, for instance, terms. That's a second part of Henk and Michael's paper, 2005. We're talking about the impact of turbulence on the low frequency, and that's typical of what's been seen in box models. So where were we at that time? If you focus on this phenomenon, that was the goal of the Caution project. If you isolate this beast under seasonal forcing, you see that it can be very strong. It can be basically the same amount as what's observed. It occupies a broad range of scales, and it has multiple imprints on climate indices. So the question was still open. I mentioned it earlier. What is the fate of this guy when you switch on back the full forcing, the full range of atmospheric variability? Would this beast be damped, be paced by the forcing? In that case, would it remain chaotic, still chaotic, or would it not be? We will see that. What is the interaction between that and the forced variability, or the forcing? And more generally, what is the atmospheric constraint on the oceanic state and on its variability? These were the open questions coming from these first results.
Could you go back to your temporal spectrum?
Yeah.
Is that a temporal spectrum at a point?
Sorry?
Is that a spectrum in time at a point in space?
Guillaume? No, it's over the box.
Averaged over the whole box.
Yeah. So, given those open questions, at that time we decided to make the Occiput project, where the goal, I mentioned it, is to look at this guy under full forcing, to investigate the stochastic behavior of the global ocean. Well, it's regional, but to look at it in the global ocean, using an ensemble simulation with perturbed initial conditions. I mentioned the word chaotic, which one definition of it is highly sensitive to small change in initial states. So let's do it. Let's force an ensemble with perturbed initial condition with the same forcing on all members. And this forcing is taken from a reanalysis. So now we can investigate the stochastic behavior of the system under observed evolution over the last decades. So that's my second part. And this is one slide explaining you the simple strategy we adopted. We did two ensembles with NEMO at 1/4 of a degree, so driven by atmospheric reanalysis. Okay, so full range of timescales. The first is global, that's a big one, and we did it between 1960 and 2015. And the second was done first, but it's a North Atlantic over 20 years. So we calibrated the system on this simulation, and then we did that. So we do some kind of spin-up at the beginning with one member. And then we initialize 50 members with the same final state here, activating for 1 year only a stochastic perturbation in the equation of state. We stop the stochastic perturbation after 1 year, ending up in 50 slightly different initial states. So we stop the stochastic perturbation and we resume the integration for the remaining 56 or 55 years. So why do we do that? Because we generate a time-varying PDF of any variable you want. Well, some kind of PDF sampled by only 50 states, but it's at least we can look at what it looks like. And when you have a PDF changing in time like this, you can compute the ensemble mean, and we named it the forced variability. The evolution of this ensemble mean is common to all members. Okay, so that's exactly what the system may respond to the same forcing seen by all the members. And around this you have a spread. It may be Gaussian, it may not be. I will show you things. So we will. It's another way to look at the intrinsic variability, which is now modulated, possibly modulated by the full range of atmospheric timescales. Okay, question at this? No? Okay. So that's one result of what we have. That's a global run. This is sea level. Each frame is taken it's a 5-day average. On the left, you've got the ensemble mean evoluting. Well, that's an evolution over the first 5 years. So this field is almost devoid of turbulence after some adjustment timescale, because the turbulence is decorrelated among the 50 members. So it comes, that's what you see here. That's the ensemble spread, the ensemble standard deviation of sea level. So you see that it reaches 30 centimeters. That's typically an instantaneous view of the turbulence in the system. So it may be interesting to look at high frequency variability of kinetic. It's not really eddy kinetic energy, but that's not far from that. So what you see here is relatively high frequency intrinsic variability. So here are two plots showing you what's going on with yearly sea level averages. The first here is taken right here in the Gulf Stream. Each of those small gray lines shows you what's going on in each of the 50 members. That's a big mess, as you can see. And its width gives you the average magnitude of the intrinsic yearly, interannual and longer variability. However, it's modulated. The ensemble mean in yellow here is modulated in time. So in this region, we have verified that the intrinsic variability clearly dominates the yearly variability of sea level in this region over the forcing. The forcing is not the main driver. In this more quiet region, the center of the subtropical gyre, where you have much less mesoscale eddies, as you can see, there is some spread at interannual timescale, but the ensemble mean modulation is much stronger. So the forcing, relatively speaking, has a much stronger imprint on the solution. So that's a way to discriminate between the oceanic chaos, to make it short, and the external forcing. Let's stay on rather long timescale, so interannual and longer, and let's focus on more integrated variables. This is ocean heat content integrated over the first 700 meters, and we focus on this range of this 31 years. So we have one map of ocean heat content for each member and each of those years, and we can animate the ensemble mean of this guy, and you see some Niñas, responses of the system to the forcing again, which looks like tripole, ANAO related anomalies in ocean heat content. That's pretty well documented in the literature. But on top of it, as you can guess, each member makes its own story. And here is what the member 5 does on top of that. So you take this total solution of member 5, you remove that guy, and you're left with this kind of thing. As you can see, the scales are not exactly the same, but it's been a little bit saturated. What you can see is the chaos generated by this member is small scale, mesoscale, typically in the Gulf Stream, in the ACC. But if you wait a little bit, you see emerging some much bigger structures which carry huge anomalies of heat, positive or negative. And these guys might have potentially a large impact if you couple this kind of model to the atmosphere. Again, this guy would be all white, this movie, if we had done it at 2-degree resolution. So it's potentially an important impact of the mesoscale, which is one of the sources of this phenomenon, on the large-scale ocean variability and potentially on climate. These are open questions. So we tried to quantify this. You can split the variability into forced, I told you how to do that, and chaotic. And with Guillaume again, we put in green the regions where the chaotic low frequency variability again exceeds the forced. So as you can see, most of the mid-latitude current extensions and up to low latitude in the South Atlantic, the variability is mostly chaotic at low frequency on this climate index. So I think it raises questions for the interpretation, if the model is right, of course. Imagine you have high quality time series here of ocean heat content, and you try to interpret it as being driven more or less by the atmosphere. What our results suggest is that most of this, a larger part of this variance, of this low frequency variance, is just emerging from the ocean itself and may not be connected to the atmosphere, or may not follow any previous atmospheric variability.
So I remember analyzing the data from the larger ensemble simulation at ENCA. That is an ensemble forced by atmospheric perturbations. They also show some like strong chaotic variance of the ocean circulation. So I'm wondering if you have checked the the deep overturning circulation and consider the possibility that the atmosphere may contribute to the chaotic variance.
Is the ENCA ensemble you're talking about coupled?
Yes.
So it's a completely different question.
Okay.
Here, the atmosphere is prescribed and is the same in all the members. So the diversity you see here, well, I showed before, is only emerging from the ocean. When you have a coupled model, that's a whole coupled model which generates, through El Niños, for instance, some phase differences among the members. So that goes into the spread, if you wish. We focus on what the ocean itself can generate with no coupling and whatsoever, and no difference in the forcing. So that's a new kind of behavior that may be added to what you see. What is seen is in a low resolution coupled runs. So what I show here is a local diagnostic, and the chaos exceeds the forcing, but it's still, the chaotic behavior is still big. If you integrate ocean heat content, yearly ocean heat content over this big box, you can draw 50 time series for each member, and you see that it's pretty different among the ensemble. So it touches also very large scales. However, there is still this atmospheric modulation of this dispersion, this chaos, call it as you want. So it's not a local thing only. And it also touches very long time scales. If you compute from the same ensemble simulation the trends, 30-year trends between 1980 to 2010 within each member in all regions, we smoothed the small features. We keep only features rather bigger than this scale. And we plot here the ensemble mean trend okay, that we have over the globe. So this is what we may call the forced ocean heat content trend. It's shared by all the members. You can also compute the spread, because there could be, and there is, a spread of trends within the ensemble. And you can make a test between the spread and the ensemble mean trend. And we figured out that in the regions that we hatched in green here, the 30-year ocean heat content trends exhibit a large ensemble spread, such that those trends, the trends you may find in one member or in the real ocean, if the model is not too bad, cannot be unambiguously attributed to the atmospheric forcing. You are actually sampling randomly either growing or decreasing phase of the multi-decadal intrinsic ocean heat content variability, because it reaches longer timescales than this. Okay, so given the member you may consider, or even the real ocean is one realization, you may, in some regions, not all of course, in some regions where the forced variability is small enough, you see it's between large forced trends and small, large in absolute values. In all those regions where the ensemble, the forced trend is weak enough, you have some big ambiguity about what may drive this trend. Is it attributed? Can you attribute it to the climate change locally? It's not sure. That's what this result suggests. So let's talk a little bit about the AMOC. Back to the AMOC, whose intrinsic variability was looked when it was isolated from any low frequency variability in the atmosphere. So only one latitude, the one which exhibited the largest intrinsic fraction under seasonal forcing, 35 south. Here there is the SAMOC project, which is currently implementing a monitoring array of the AMOC, just as it's been done 10 years ago or so at RAPID. So it's being deployed. That's a region where the spread that you can see here, that's the yearly AMOC with the ensemble mean and each realization here. So it seems to be spreading quite a bit, and this is confirmed here. So I'm not going to talk about all this, but this is a STD, standard deviation of the forced variability. That's the black line. And you see it's something like half a further at interannual timescales. And here is the time-varying spread of the ensemble, whose temporal mean is extremely similar to the force. So it's a confirmation under full forcing that roughly half of the variability of the AMOC there is forced, and the other half is kind of random. The phase of this random contribution is random among the members. Okay.
What is the average for the transport here?
There, it's in the paper. We showed the mean. I don't remember. Maybe 18 or I don't remember. You can also decompose, so I won't go too far into that, but just to show what kind of thing we're trying to do, we can put for each latitude, again, we are between 70 north and 35 south. For each latitude, you can compute a frequency spectrum of the forced variability, so of the ensemble mean, AMOC variability, and of the noise which goes around this ensemble mean, of the intrinsic or the chaotic part. So the colors show you the frequency spectrum. So you have decadal and multi-decadal variability in the North Atlantic, which is expected from the forcing, okay? And these scales are actually coming higher. I mean, the higher frequencies over there in the low latitudes as expected as well. And here there is a maximum which doesn't show up here, but there. As we saw, the mid-latitude currents, like the Gulf Stream, are a hotspot of low-frequency chaos. And here are the scales which are concerned. It goes from something like 2 months up to, you see this red thing, it goes to 10 years or so, it decreases there. But in the South Atlantic, there is a real big hotspot, which goes as far as let's say almost the equator. This is a retroflexion of the North Brazil current here, and the contours here tell you the fraction between this guy and that guy. For instance, within these dashed contours, half the intrinsic variance represents half of the forced variance. And here it's 100%. So the intrinsic variability exceeds the forced variability in these bands of latitude and frequency. So that's what kind of diagnostic we can see to help us eventually interpret what we see in the data. Okay? A last example of what we've done is just to illustrate what's going on in the model. This is the forced AMOC interrenal variability, one color per year for 56 years or whatever. So you've got all the members exhibit a strong increase of AMOC in this band of latitude, and before that it was further south. And you see some very large meridional coherence. And this is what's going on top of this in one member. It looks the same in all members, but the phase would be different. That's what characterizes the chaos in this system. So you see some typical, some similar, there is some similarity between the two. So it raises quite interesting questions, and we have split this signal into the leading EOFs. You see the leading EOF peaks in the northern subtropics in the Atlantic with a negative lobe in the intergyre, if you wish, and others. And maybe something interesting. Here are the leading two EOFs of the intrinsic chaotic variability. The first, and by far it's a 43% of the interrenal variance, has a one-signed mode and corresponds to these very meridionally coherent anomalies, and peaks in the South Atlantic. So it gives you a feeling of what this guy is structured, how it's structured. Maybe just to mention, we did from the regional ensemble, whose southern boundary was here, 20 south, and all the fields were relaxed toward climatology. You couldn't have any intrinsic variability here, so it's 0 there. And this mode disappears. This mode remains there, a bit distorted by this southern boundary, but this guy becomes the first one, suggesting that this mode has an origin, let's say, in the South Atlantic and perhaps in the Southern Ocean. So these are investigations underway, trying to see better where this guy comes from. And it's clearly a dominant signal, which is quite big. Okay, well, these are recent results from this big ensemble. There is a lot to be done. And however, we have some new stuff which are a little bit more maybe interesting and intriguing, or we're trying to find some ways to investigate this. We are back to high frequencies. This is daily sea level, okay, daily sea surface height in the Gulf of Mexico at the entrance, and we're going to look at what's going on here. These are just trajectories of observed drifter, so it's not modeled, just to illustrate where we are. This is SSH for 1, 2, 3, 4, 5 years at daily time series, and all the little things you don't see, but believe me, I could zoom in, represent what's going on in each member. The black line is the ensemble mean, so it's kind of modulated. If you accumulate all this information into one big PDF, taking all the days, all the members, you can build a PDF like this, which looks kind of Gaussian. And if you take any time and you superimpose the PDF of the response of the system, it's basically Gaussian as well. So what's going on is you have some kind of Gaussians which are modulated here. So you can see that as a Gaussian noise which is modulated in time by the forcing. Okay? It's not that difficult to represent intellectually. That's noise which is, well, modulated, pushed up and down by the wind stress curl or stuff like this, or waves or stuff like that. But we are in a completely different world there. We are in right where the loop current regularly expands like this. When it expands, you got the SSH coming up because that's a high SSH, and then eventually it sheds eddies, which goes to the west. And in other times, you've got the loop current, which goes straight into the Gulf Stream with no high here. And in the literature, you can see two views. Some people focus on the dependence of the shedding of eddies to forcing. Some others would more focus on the chaotic nature of this variability, and basically it's not very clear. It seems to be both random and both influenced by the forcing. If you focus on the last 5 years of this North Atlantic ensemble simulation, here you see each of the SSH time series at this point in each member. And you can see that there is always a member or several in each state, high or low. Again, if you accumulate all this information in one PDF, you see a nicely bimodal behavior. So you have two preferred equilibrium states. Okay? So investigating the evolution of the proportion of modes of members which are in this mode or that mode, or does the system remain always equally split between those two modes, or is it strongly constrained? This can tell us something, I hope, about the influence of the atmosphere on the turbulent ocean. And focusing again on the temporal evolution of this, here is an example of what we are currently trying to do. Focus on this date, for example. Well, we have a majority of members in high state, high SSH, a few down there, and you may sketch the instantaneous PDF as this, more members in high location. So we have to investigate this evolution in a probabilistic way. We are trying to use the information theory, simple concepts from the entropy, for instance, that we compute every day from such PDFs. We normalize it by the climatological PDF for normalizing reasons. And you can do that at every XY point and every day. That's what we've done. And you can build an index like this, which goes from 0 to 1. When this guy is 0, the entropy, the instantaneous entropy is 0. So all the members are in the same state. So that's absolute control of the ocean by the atmosphere. The members do not see any chaos. They do the same. On the opposite, if the entropy is maximum, which means exactly as big as this climatological, then the atmospheric variability has no impact on the dispersion. Okay? So in this index, when it's 0, you have no chaos, if you wish. When it's 1, it's a maximum. And the forcing constraint is maximum there and is absent here. And if you animate this S index in this region, here is what it looks like. So in all those regions, it's generally red most of the time, which means that the dispersion of the system, whether it's Gaussian or not, this index doesn't mind if it's Gaussian or not, the dispersion is maximum, whatever the forcing does, okay? But in some regions or moments, like in these blue phases, you've got a restricted, smaller dispersion than usual, which means that the forcing, this is our interpretation, the forcing has had some strong influence on the dispersion and has, like here, has increased its constraint on the ocean. Another example is the blinking blue thing around the Gulf of Mexico. They actually coincide with the hurricanes and strong storms, where all the members go into high SSH. So sea surface surges, how do you call that? Surges, coastal surges, and all the members do the same. So the entropy gets very, very small.
What happened when we have seen everything becoming blue at the same time?
That was a spin-up, just the initialization of the ensemble. It takes, depending on the regions, it takes a few years, well, here, to get the maximum spread, statistically speaking, and it goes much faster in the Gulf Stream. And this index actually exhibits, this is a Hofmüller diagram, it's longitude time, and there is some propagation of information. That's really an information statistics, and you see that some entropy minimum is coming into this domain here and then propagates into this region. So I would like to investigate how the turbulent impacts or the chaos, which is generally spontaneously generated by the ocean, actually influences what's going in here or downstream in the Gulf Stream or stuff like this. Well, what time do I have? Oh, maybe I should skip well, maybe if you're interested about what we're thinking about. Okay, this is a forced ocean model strategy, and we have done 2 ensembles a little bit different, and we have some ideas about how the chaos may be influenced by our atmospheric forcing strategy, or whether it may not be that much influenced, and potentially ideas about how this guy may potentially impact on the atmosphere in coupled mode. I just wanted to mention that I focused on SSH, AMOC, SST, whatever, but actually these are modes, multivariate mode, which concern basically a lot of variables together, a lot of depth. These are organized modes that we are trying to investigate now. So maybe I should go to the conclusion now. It's time. And just try to summarize. So what these studies suggest is the low frequency ocean variability can be seen in different ways. Usually it's been studied in coupled mode or in forced mode in laminar model without turbulence. And in that case, we have seen that it's almost 100% forced. If you submit such a model to a repeated seasonal cycle, it will do exactly the same. There is no low frequency variability emerging. So deterministic hindcasts, when you put a reanalysis on top of such a model, if it's deterministic, it's okay because there is no noise coming in out of the system. But it's completely different when you are in an eddying ocean model. Again, to make it short, I call it atmospherically modulated chaos. You have a lot of things coming out of the system, especially in the mid-latitudes, but it may be modulated by the atmosphere, more or less, sometimes barely not, and it affects a lot of climate indices. So I think there is something important for to look at for climate variability. This chaotic signal is strong, goes to very long time and space scales, and it's still complex and poorly known in OGCMs. There's been studies in idealized context, but not much in complex geometries and stuff. But in this case, I think probabilistic simulations are required, because if you take one simulation, it's not the final world is not there. You just change a little bit the initial conditions. In a lot of regions, you will have something quite different in terms of phase. So there are a lot of open questions. It's not a square box, it's more complex. So there are potentially multiple dynamical processes involved in that. We don't know the energetics of this. We have started a bit with Guillaume, but there is a lot to be done. So I believe that such realistic global ocean models may not be the easiest way to start with those investigations. We should, or someone should think about that with idealized simulations, maybe GFD studies and stuff like this. I'm concerned about what is the implication of this stuff on the interpretation, the detection, the attribution of observed climate variability in the ocean or climate change. You've seen that these 30-year trends are actually uncertain. So I think there are some open questions to be looked at, and we've generated 50 series of synthetic observations in situ and satellite, and we can therefore, for each observation, we can build a PDF taken from the model Ensemble, and maybe depending on the shape and the width of the PDF, say, all right, this observation at this point seems to be more or less representative of the forced influences. I mentioned this question, which I think it's also potentially important. This stuff touches SST ocean heat content over a wide range of scales. It should influence SC fluxes and perhaps atmosphere and climate. So we're trying to think, maybe instead of investigating, but thinking about how to progress, first looking at how the RC fluxes could be sensitive to that. And just to summarize, some subsets of the big, it's a big data set, but some subsets may be shared, and if you are interested, just let me know. We are open to collaborations, and I leave you with a few papers if you are interested in that. And I thank you for your attention.
Do you have a question?
Just a very quick question. For the low frequency variability in the ocean, is there a coherent spatial pattern that associated with those things, or they're not quite related?
I showed on the AMOC that you have highly coherent basin scale or gyre scale at least, but also basin scale on long time scales. This intrinsic variability is structured. It's also the case in terms of isopycnal anomalies, ocean heat content. It's not grid scale, clearly not. You have Rossby modes, you've got a lot of things like this.
I'm afraid I missed one of your arguments. Could you please repeat why you have a cascade of variability to low frequency? You had an argument about that at some point.
Well, you have merging of eddies during their life cycle, and they merge, they grow. So that's the source of the well-known spatial inverse cascade. Things grow in space. But, well, it's not our contribution, but more recent studies have shown that there is something similar occurring in time. High frequency stuff feeds lower frequency stuff, probably through the same kind of process. So I'm not a specialist of that, but we have contributed to diagnosing.
Did your low resolution models have any parameterization for the mesoscale eddies? And if not, then would that somehow be able to capture any of this chaotic behavior?
We are using, in the 2-degree simulations we've done, under seasonal forcing, we were using GM, okay? We were using GM, so that's classical subgrid scale parameterization, which doesn't generate much. I mean, those things are made to flatten isopycnals, but it's more, there is more to it when you actually resolve things, even partially. You have some upgradient fluxes, you've got, it's very different, really a different world.
So, is this working? So this temporal inverse cascade, and my interpretation of that would be that you have an inverse cascade in space, so you get bigger eddies, and they will sort of automatically have a longer time scale, so you're bound to get an inverse cascade in time. It looks to me like your spectral slope in time is steeper than that, because you're actually exciting longer scales, the large scales, than you would expect from a purely spatial inverse cascade. It seems like you're getting this, eddy merger and creation of large scales. When they get to large scales, they're starting to do their own thing, if you will. They're having dynamics a la Gill and Dijkstra and so on, so they have these long time scales, and those have been generated by a kind of spatial inverse cascade, but when they get to large scales, they're doing their own thing, which is generating the large scale, the long time scales, and so it'd be kind of interesting to see whether your spectral slope in time is steeper than you might expect from a classical argument, and that's...
Yeah, that's an interesting suggestion. I know that Brian Arbeck discusses the relationship between spatial inverse cascade and temporal inverse cascade at the end of his 2014 paper, and mentions that it's connected, but it's not straightforward. There are some differences, but again, I'm not the specialist of this.
This may be something you were going to talk about but skipped over because of time, but historically, one of the reasons people have been leery of this kind of ocean only simulation, especially for low frequency, large scale modes, is that their sensitivity to the way you formulate the boundary conditions. You haven't said how you're restoring surface temperatures or salinities, whether it's mixed boundary,
That's exactly what I
strong
skipped.
forcing of, and that affects the variability of the ocean model. And you sort of skipped over a pretty important thing that historically has prevented people from doing this.
That's exactly what I skipped there. I can tell you quickly, maybe pieces of answers. We did 2 ensembles in the North Atlantic. The first is composed of members which are driven individually through bulk formulae. And in this setup, as you guys probably know, the turbulent heat fluxes, so the tendency on the temperature for member I, is equivalent to some kind of relaxation to an equivalent air temperature, because there is a feedback, there is a typical time scale on which the ocean temperature goes to the atmospheric temperature. In this ensemble run, again, each member is driven with individual AC fluxes. So if you split temperature into ensemble mean and ensemble anomaly, you can convince yourself that the ensemble mean temperature, so what I call the forced temperature, is relaxed toward this guy, but that the actual tendency of the spread are negative, which means that the temporal evolution of the spread here is negative. You damp the SST spread, We did another example where each member is driven by the ensemble mean of RC fluxes. So each member sees exactly the same fluxes, okay? And you can, in this case, the ensemble mean turbulent heat fluxes, if you split the signal like this, you can show that the ensemble mean SST is relaxed exactly as before, but the chaotic spread is no longer, the SST spread is no longer constrained. But maybe what's most interesting is, I think, here is the spread you have at the surface, SST, with individual forcing, so it's very weak. You multiply it by 5 if you free the SST spread, doing an ensemble average. But what is interesting is that at 500 meters, the temperature spreads look very similar. So the forcing method that we have used in the global run is driven like this, indeed is expected to underestimate the SST spread, and to some extent the ocean heat content spread as well. But if you go deep enough, you see that the spread doesn't care much, which I think means, or strongly suggests, that the source of the spread is located down there. It's at the depth of the thermocline. This is where eddies emerge and have most source of potential energy. And then there is a damping towards the surface of the temperature spread, in this case, and not really in that one. So we are concerned by this issue, and I wonder whether the real ocean atmosphere system lies in between. In this case, it's just like if the atmosphere wouldn't care about strong, low-frequency SST anomalies emerging spontaneously, it would damp them back. In this case, that's the other extreme. Well, the atmosphere wouldn't have any impact on an SST deviation, which is chaotic, emerging from the system. I guess the real ocean atmosphere coupled system is in between. But these are really quite recent results. I don't know much to say more.
Okay, so thank you again for this very interesting topic.
Thank you.